Okay, we're officially on the air. Well, how's everybody doing tonight? How are we doing on the practice tests? Anybody taking any this week?
I've taken a couple.
How you doing? What kind of scores you getting?
Not very high.
Well, it's okay. We're only halfway through the class. So if you're getting around 30, 40%, you're okay. Anybody else take the test? How are
Yeah,
we doing with it so far?
I took one not too long ago. I think got like 72%.
Oh my goodness. Wow, you're way up there. Good job.
Yeah, my grandpa actually got me the study thing, and I did that for about a month and a half. So I already
Oh,
had some practice.
oh, okay. Well, good. Sounds to me like you're about ready. Okay, anybody else?
I hit 70% twice in the last week.
Oh wow, that's good. Wow, you're doing great. You're just about ready. Okay, anybody
And
else?
the math is easy. I have an electronics degree, so that was
Oh, okay, so this part's probably pretty basic to you, huh? Well, good. Well, I would like to encourage you to keep taking the practice test. The more times you take the test, the better you'll get at it. And hopefully your scores will gradually get better and better. But we still have, well, counting tonight, we got 5 weeks yet, so we still got plenty of time. Okay. Any questions or any concerns about last week's what we went over? Okay, well, let's go ahead and get started. There we go. Now we can see. Oops. There, that's better. Okay, so purchasing a radio. I think I may have mentioned before, and I tell people all the time, this is a hobby that you can spend as much money as you want to. So I would really encourage you to don't spend a lot of money until you know where you're going with it. Because ham radio has so many different opportunities, so many different kinds of things you can do. So until you kind of get a feel for where you want to go, I would say start out pretty cheap. You can get these little Chinese-made radios that called a Bofeng, and I've seen them as low as $40, and they're half decent. You know, they're not top of the line, but they work. So you can start out with something like that, and then if you want to, you can gradually move up into something you'd like a little better. So and I would really encourage you to go ahead and get your radio. You can either purchase one. Sometimes you can even find loaners. A lot of the ham radio clubs will loan you a radio until you can get your own. But like I say, start out small, just a little bit, and then kind of see where you're going to go with it, and you can go from there. Um, and like I say, radios. Some of these radios you can get for 40, $50 pretty easy. And you can also get radios that are in the thousands of dollars. So yeah, just get a little small radio to start with. And you can actually go ahead and get your radio, get it programmed, and start listening. You don't have to have a license to listen. The FCC rule says that you can listen to anything that you have the ability to listen to. If you have the technology and you can listen to it, then you can. If somebody doesn't want you listening to their traffic, it's their responsibility to make it so you can't hear it. And there are things they can do. They can encrypt it. They can make it hidden so that other people can't find it. So, but yeah, if it's just an open channel, you're welcome to go ahead and listen to it. It's just like in the days, when you used to be able to turn on a scanner and listen to the police department, the fire department. As long as you don't talk on it, it's perfectly legal. You can listen to anything that you can pick up. So yeah, if you go ahead and get your radio, get it programmed up, and just listen to what goes on out there. Listen to how people talk. Listen to how they do it. So you kind of get a feel for it. Okay, I want to introduce you to the metric system. Some of you may already know it and some may not, but everything in electronics is all metric. That's the only system they use. And once you learn the metric system, it's really easy to use. Um, in the metric, the way they do things, they have multipliers on all of their numbers. And some of these you might be familiar with, like deca, that means tens. It's a multiplier of 10. It's like decade. A decade means 10 years. Hecto, I've rarely ever heard that one used, but that means hundreds. And kilo, you've probably heard that one before. A kilo means thousands. So if you have 1 kilowatt of power, that's 1,000 watts. If you have 1 kilo ohm, that's 1,000 ohms. Um, and and that one, it's used a lot in a lot of different things. Mega, you've probably heard that one before. And mega means millions. Like in computers, you have megabytes, mega, you know, for storage on your disk and so forth. Mega means millions. And giga, you've probably heard that one in computer talk. You talk about gigabytes, and your hard drive is, 10 gigabytes or 100 gigabytes. And giga means billions with a B. And then tera means trillions with a T. So those are just multipliers. And then if you get on the other side, over here on the right side, you get into the decimals, where 1/10 is a deci. That one's not used very often, but like a decimeter or a decaohms or something, that means a tenth of an ohm. A centa is 100th, and that one's not used very often either. But milli, that one's pretty common. Milli means 1/1000th. We have milliohms, we have milliwatts, we have milliamps. It just means 1/1000th of an amp or 1/1000th of an ohm. And micro means 1 millionth. You've probably heard that one before. Micro ohms and micro watts and micro, not a microwave, but well, micro, yeah, micro means 1 millionth. But yeah, it's 1/1 millionth of something. And nano is 1/1 billionth. And that one we use a fair amount in electronics, but it's not used in the technician course. And then pico means 1/1 trillionth. It's 1/1,000,000,000,000. Now, the ones that you need to be concerned with for this course is basically the kilo, the mega, and the micro. I think those are the only ones that are used on the technician test. So a kilo means thousands. So if you have kilo ohms, that's thousands of ohms. If you have kilowatts, it's thousands of watts. And mega, of course, means millions. If you have millions of ohms or millions of watts, those are measured in mega. And then micro means 1 millionth or 1/1 millionth of something. So you do need to be familiar with those because they do use them and they're going to be on the test. So you kind of need to know what it means. The metric system is actually, it's pretty simple. Let's take a number here, 1,350. Okay, in the English language, we would say 1,350. That's how we read that. But in the metric system, that would be 1.35 thousand. Okay, so the decimal becomes a decimal, I mean the comma becomes a decimal point, and it's 1.35 thousand, or we would say 1.35 K. K means kilo. So that's how they do it in metric. It's a way of shortening it so that you don't, have all these long strings of numbers and have to say it all out loud or write it out loud. And we can actually multiply and divide and add with the multipliers on there. So here's another one, 1,150,000. So in the English language, that's how we would say that, 1,150,000. But in the metric system, we would say 1.5 or 1.15 million. So again, the decimal or the comma becomes a decimal point, and we drop off the last 3 zeros and put a meg on the end, a mega. So it'd be 1.5 or 1.15 mega, which is 1.15 million. Okay, so it means the same thing. It's just we say it differently, and we use it a little differently. So you do need to be familiar with those, at least those three. The others, you know, if you get more into electronics, the others you'll need to know too. Oops. There we go. Okay, let's talk about the speed of light. Does anybody know what the speed of light is? How fast does light travel?
182,000 miles per second.
Yep. And if we put that into metric, that becomes 2,888. 2,888, I think it is. Don't quote me on that. But in electronics, we use it in the metric system. Now, for the purpose of this test and for the purpose of the technician, we can just round that off and say 3 million. So the speed of light is 3 million meters per second, or slightly less. I think it's 288 if I remember right. Oops. Box keeps stopping. There we go. Okay, so I'm going to do a little demonstration here. And I apologize that for some reason these pictures are really dark. I don't understand why it's doing that. It's not on my end, but I think on your end it's quite dark. So I'm going to kind of show you wavelength and frequency and how those are related.
Okay, for this demonstration, I want to talk about frequency and wavelength. This is something that you're going to hear a lot in the ham radio world. It's true for any radio transmission, but the ham radio people use it a lot. So I'm going to do a little demonstration, and you have to promise not to laugh at my silly little gadgets that I make to try to demonstrate something. So we're going to make a wave machine here. We're going to create waves. Let's see if we get this down here. Okay, so what I'm doing is I'm creating some waves here. Now the frequency is generated here. This is how many times this is going up and down to create the waves. And the actual waves are going out here. And you can see here the waves are about that long. So that is the wavelength. That's how long each wave is. Now when you create frequencies, the waves transmit out into the atmosphere. And if this had the capability of going all the way out the door, across the street, and all the way to City Hall, that wavelength would stay the same all the way down, even though it gets weaker and weaker and eventually will disappear, but that wavelength never changes. Now, if I increase the frequency, get it to work here. Okay, there we go. So now, let's go a little bit faster. Okay, I don't know if you can see that or not, but now I've made it go faster, and now the wavelength is about that long. It's shorter than it was. So as the frequency goes faster, the higher you get higher frequency, the wavelength gets shorter. And of course, as the frequency gets lower, the wavelength gets longer and longer. And we talk about wavelength a lot. Wavelength is just another way of saying frequency. So by this, you can see as we change the frequency, it's going to change the wavelength as well. And like I say, that wavelength stays the same all the way wherever it goes. Okay, so now let's go back and we're going to talk about frequency and wavelength. So we'll go back to the classroom for that.
Okay, so hopefully you could see enough of that to kind of get the idea of it. So frequency and wavelength really mean the same thing. It's just a different way of saying it. So the frequency is how often, well, actually, let me go to the next picture here. So the frequency is how many times it oscillates back and forth per second. And the wavelength is the distance from one peak to the next. And so every frequency has a wavelength. And we can very easily calculate, if we know the frequency, we can know what the wavelength is. Or if we know the wavelength, we can find the frequency. So I got one more formula for you. I know it's, oh, wait a minute. I'm not quite to it yet. So the higher frequency, as you can see, the wavelength is much shorter. See here, this is looks like about 1¼ squares here. Okay, so that is the wavelength at this higher frequency. And the frequency is, obviously going faster. So we get a lower frequency, and you can see the wavelength is about 2½ squares. And then as it gets lower and lower, it's going to get this wavelength that's going to get longer and longer. Okay, so converting frequency to wavelength and wavelength to frequency. There are some test questions about this, so you're going to need to know how to calculate. Typically what they're going to do is and I'm going to show you what the different frequency bands are, and they'll give you a frequency and they'll say what frequency band is it in. So you have to convert it to wavelength to see what the frequency band. Okay, so the actual speed of light is 288 million meters per second. But for this class, we're just going to round it up to 300, just to make the math simpler. It's not going to change our answers very much. Okay, here's the formula. It's 300 million or 300 mega divided by either frequency or wavelength. So the 300 million, that's, okay, that's the speed of light. And if we want to know what the frequency is, we can take 300 million, divide it by the wavelength, and it will give us the frequency. Or if we take 300 million, divide it by frequency, it will give us the wavelength. Okay, so let's do something simple. Let's go into the 2-meter band. So we know the wavelength is 2 meters. So what is the frequency? So you take 300 million, divide it by 2, gives us 150 million or 150 megahertz. Now, if you want to double check your answer, what you can do is take frequency times wavelength, should come out to 300 million. So if the frequency is 150 megahertz, the wavelength is 2, so 150 times 2 is 300. Okay, so it's a very simple formula. It's just whatever you divide by one of them, and it will give you the other. And there again, we can, let's say if we have 100 megahertz right here. This frequency is 100 megahertz. So 300 mega divided by 100 gives us 2. Whoops, no, that's not right. No, I was going to use something different. Okay. Well, anyway. But yeah, if we just use the 2-meter band. So, 2 meters, 300 million divided by 2 gives us 150 megahertz. So we know what frequency band it's in. Okay, I'm going to show you the different frequency bands in the ham radio world. And this is how they typically describe the band, whatever frequency that you're working with. You might hear people say, well, I'm working in the 160 meter band. Okay, what does that mean? Okay, the 160 meters goes from 1.8 megahertz to 1.9 megahertz. So there again, if you wanted to take see, we can calculate the exact amount. Oops. So if we take 300 300 million. We're going to divide it by 160. And that will give us 1.875. So that 1.875 is right in this between 1.8 and 1.9. Now, when you calculate it, it may not be exactly on. It might be off just slightly, but it's because we're using 300 instead of the 288. But it'll be close enough that you'll be able to identify what band it's in. Okay, so some of the other bands, the 80-meter band, this is a very popular one. A lot of people use this one. And that's from 3.5 to 3.6 megahertz. And you see the bands are very small. They're very narrow. But you can still have 3 or 4 different conversations going on in there. 60 meters is 5.3 to 5.4 megahertz. That's also a pretty popular one. A lot of people do that. 40 meters, that's another popular one, 7.0 to 7.125 megahertz. And you don't need to memorize the exact, start and ending point of each. As long as you can, if they give you a frequency, you can identify which band it's in. 30 meters is 10.1 to 10.15 megahertz. 20 meters is 14.0 to 14.3 megahertz. 17 meters is 18 to 18.2 megahertz. 15 meters, 21.0 to 21.2 megahertz. And then up here we go to 12 meters. It's 24.8 megahertz to 25.0. Now 11 meters, you probably already know what this is. This is the CB radio band. CB radio is actually part of the ham radio band plan. And where that came about is many years ago when the FCC allocated all these frequencies for ham radio use, people were saying, well, hey, why can't we have just one frequency band that we can just use without a license, just for everybody that doesn't require anything. So the FCC said, all right, we'll give you the 11-meter band. So it's 27 to 28 megahertz. And that's where CBs are. And they're still there today. They operate in this band right here. 10 meters is 28 to 29.7 megahertz. Now 10 meters, you can actually, 10 meters and 11 meters, with your technician license, you can operate in the 10-meter band. You can't go down into any of the others. You have to have a higher license for those. But you can operate in the 10-meter band. 6 meters is 50.0 to 54 megahertz. And 2 meters. And like I say, this is where most of you are going to start out. When you first get your radio, you're probably going to be in the 2-meter band. And the 2-meter is by far the most busy of all the frequency bands there are. Everybody has 2 meters. And you're going to hear a lot of nets. In fact, just earlier before we started the class, I checked into a net, and that's on the 2-meter band. So you're probably going to get a radio that's going to have 2 meters in it, and it's a good starting place. It's a good place to kind of learn a little bit, and then if you want to, you can advance, get a higher license, be able to go into some of these other frequency bands. There's 1.25 meter band, which is sometimes referred to as the 220 megahertz band, because that's where it is. It's in the 220 group. Now 70 centimeters. Now you notice that this one has centimeters instead of just meters. Okay, a centimeter is 1/1000th of a meter. So it's actually the same thing as 0.7 meters, or we very often call it 70 centimeters. So centimeter is just 1/1000th of a meter. Okay, and that's in the 420 megahertz to 450 megahertz. We sometimes call that the UHF band. And there is a fair amount of traffic there, but not as much as the 2-meter. So if you do get a dual band radio, most likely it's going to have the 2-meter band in it and the 70 centimeter. That's the dual band that most people use. that gives you the ability to talk in either one of those bands. So dual band radios are very popular in ham radio. A lot of people have them. A lot of people like them. And then we have the 33 centimeter, and that jumps all the way up to 900 megahertz. So between 450 and 900, there isn't any ham radio activity at all. There's no ham radio frequencies there. So there's a pretty big gap between there and the what we call the 900 megahertz band. And then there's a 23 centimeter, which is really short, and that gets clear up into the 1.3 gigahertz. That's up into microwave. And there are some ham radio bands that are in the microwave range. And some people get into that, and that's a good thing. But like I say, you kind of need to know where you're going before you buy a whole bunch of equipment. So those are the basic bands that we have available. Now, what I want to do is show you what's called a frequency spectrum. It will kind of paint a picture to show where everybody is and where we are and how do we fit in the grand scheme of things and so forth. So this is not anywhere as close to everything that's out there. I'm just kind of hitting some highlights just to give you an idea. So we're going to start out with the AM broadcast band. That's the old AM radios that you probably still have some of them around. Okay, that's the lowest broadcast frequency there is. It's 0.5 megahertz to 1.6 megahertz. It's in what I call low band. And then we have the FM broadcast radio, and that's from 88 megahertz to 108 megahertz. Now, way back in the early days, that was the entire spectrum right there. The technology only went to about 100 megahertz. So they split it up into three groups called low, medium, and high frequency. And today we still use the same terminology. You'll hear a lot of people that are saying, well, I'm working in the HF band, or I use the HF band, or I have an HF band radio. Okay, HF means high frequency. And that comes from those very, very early days of low, medium, and high, which now we are far, far beyond that. So that HF band is all the frequencies way down in those very low frequency ranges there. Then after technology expanded, things got better and there was improvements. They went into what's called the VHF, and that means a very high frequency. And up in there, there's a lot of public safety, a lot of police and fire and sheriff and some of those things up in there. They're up in what's called the VHF band. And ham radio has a VHF band also, but that's what it means. It stands for very high frequency. And of course, back in those days, that was as high as it went. You couldn't get anything any higher than that. And then as technology improved and circuits improved, radios improved, they developed what's called the UHF band. And that means ultra high frequency. So we went from high frequency, well, we went from low to medium to high, and then very high, and now ultra high. And later on, they opened up this to public safety. It's 450 to 470 megahertz. And most of the public safety, the police, fire, sheriff, ambulance, and all that, they moved up into the UHF band because the VHF was just so overly crowded that there was just no room for anybody. So they all moved up into the UHF band, and they've been there for quite a few years. And then after that, now we have broadcast television. Now, broadcast television is a huge, they have a huge footprint on the spectrum. They take up a lot of the bandwidth. It's not quite as much now as it used to be, but it's still a very lot. So they basically go from 470 megahertz all the way up to 700 megahertz. It's just a very huge chunk of the frequency band. And then up here, just recently, you may have remembered, what is it, about 10, 15 years ago, I guess, when television went digital. So when television became digital, they were able to shrink their broadcast band down considerably. They made it much smaller than it was. So what was the 700 to 800 megahertz band was in television. They gave that up, and so now that has become public safety. So a lot of, not all, but a lot of the police and fire and sheriff and ambulances and so forth, they have all moved up into the 700 megahertz band. Um, so that's where most of them are now. So now the VHF and the UHF aren't so crowded because a lot of the heavy users have moved on up. And then we go above that, you get up into cellular, and that's from 900 megahertz to 1.5 gigahertz. And actually, it's expanded more than that now. It's up into the, what, 2, 3 gigahertz range now. So cellular is basically everything from 900 megahertz on up. Um, so cellular's always been way up at the very top end of the frequency band. So those are just some highlights. There's hundreds and hundreds of other things in between there, but that kind of gives you an idea of where things are spread out at. So now let's see where do we fit into all this? Where does ham radio fit into this grand scheme? So if we start back at the bottom, remember I showed you those frequency bands, the 160, the 80, the 60, and the 40. Okay, all of those are down here. They're between the AM broadcast and the FM broadcast stations. Most of the ham radio people call it high frequency, but to me it's low band. It's very low frequency. But yeah, it's way down there, down near the AM broadcast. And then also the 30, 20, 17, 15, 12, 10, and 6 meter bands. Those are also down in that medium range, and it's still between the AM and the FM broadcast band. So there's a whole bunch of channels right between the AM and the FM broadcast bands. Excuse me. And those are actually very low frequencies. Your AM, FM radios that you listen to for entertainment, those are very low frequency range. Okay, and then if we go from there, let's go up to the 2 meter band. And again, this is probably where most of you are going to start out at. And that's in what we call the VHF. It's very high frequency. And it's just below the, oops, it's just below the public safety. Public safety is from 150 megahertz to 174. The 2 meter band is 140 to 150 megahertz. So it's immediately below the public safety band. And then the next one is the 1.25 meter band, which is kind of in the middle of the VHF band, or that's the one we sometimes call the 220 megahertz band. That one's not used a lot, but it is available and some people do have it. And then from here we go up into the 70 centimeter band. And this one again is just below the public safety band. Public safety is from 450 megahertz to 470 megahertz, and the ham radio is 440 megahertz to 450 megahertz. So it's just right on the bottom end, the lower end of the UHF band. And then from there, we skip all the way up to clear up to almost a microwave. And there's really nothing between the 70 centimeter and the 33 centimeter. There's just no ham radio activity in there at all. So the 33 centimeter is right close to it's just right below the cellular range. So it's up there pretty high in frequency. And that's kind of specialized things. Not very many people have that kind of technology, but there are some things up there that you can play with if you'd like to. And then we also have the 23 centimeter, which is actually up into what we call microwave. There are some microwave things in ham radio. There's people that have microwave dishes and they're able to transmit signals from point A to point B, and some fun stuff to play with. So that's kind of where we fit into the whole grand scheme of things. Okay, so, and I wanted to show you, this is actually a test question. I don't really agree with what they say, but since this is what's on the test, you have to learn what they say. So according to ham radio, the HF band, that's what I call the low band, goes from 3 megahertz to 30 megahertz. They kind of like the number 3 for some reason. So that's, by definition, that is the HF band from 3 to 30. And the VHF, the very high frequency, goes from 30 megahertz to 300 megahertz. And again, it's, all multiples of 3. And then if we go into the UHF band, it's 300 megahertz to 3000 megahertz, which is 3 gigahertz. So they've kind of divided it into those three, but that's by definition of ham radio, so you need to learn it this way. I don't quite see it that way, but that's okay. I'm not writing the test. Okay, this is what we call a frequency spectrum chart. This is in the United States, and I know you can't read it. I can't even read it either. But it starts out at the top. This is the very lowest frequency. This is the AM broadcast band right here. And then I think the ham radio is the gray one. So the ham radio stuff is right here. And this is the FM broadcast band. So we have a whole bunch of stuff right in this range here. This is very, very low frequencies. I call it low band, but ham radio calls it HF. So there's a whole bunch of things right in here. But for that, you have to have a higher license. You can't do it as a technician. You have to either get the general or the extra to operate in those frequency bands. And there are some other things up in here, some commercial stuff. And as we go higher in frequency, you notice it gets more and more busy. We go up into here, and the 2 meter band is, I think it's going to be that gray box right there. I think that's the 2 meter, the 140 megahertz range. And oh, I told you wrong. That's not the FM band. Actually, I can't quite read it. But anyway, the 2 meter band is somewhere in here. This blue right here, this is broadcast television. And as you can see, it's huge. It takes a big, big chunk. And it's not only here, but it's also here, and it's here, and it's here, and it's here, and here, and here. So television really eats up a whole lot of frequency spectrum. And then as you see, as we get higher in frequency, it gets more and more crowded. There's lots and lots of stuff in here. Most of this is commercial stuff. There is some ham radio. I think there's some ham radio right there. And then you can see it just gets more and more crowded up here. And we get all the way up into up near the gigahertz range. And there's a lot of stuff up in here, a lot of users, a lot of different applications and so forth. And then this gets clear up into cellular and up into microwave and so forth. So that's kind of how this frequency spectrum works. And it's been that way for a long, long time. Okay, so now we're going to talk about modulation. So modulation is the way to put voice onto what we call a carrier. Carrier is when you just transmit over the air, but there's no voice on it, just a plain carrier. So how do we put the voice onto that carrier so that our voice will travel along with the signal? So I'm going to do a little demonstration here and show you some things.
Okay, for this demonstration, I want to show the difference between AM and FM. AM, as we talked about, is amplitude modulation, and FM is frequency modulation. And I have a little CB radio here, and if you look on the scope right here, you can see the amplitude is the height of the signal. Test, 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 1, 2, 3, 4, 4. Okay, it's not tracking very well, but you can see the amplitude is going higher, and as a result of the audio. But when there's no audio, there's no amplitude there. Test, 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 1, 2, 3, 4. Now, the FM, we can't see the FM on the scope because the frequency shift is so small that you can't actually detect it on there. So I'm going to do a little model here for you. This is our frequency here, and this is the number of cycles per second. So with frequency modulation, the audio will actually change the frequency. We get a higher frequency and we get a lower frequency. It causes the frequency to shift just a little bit, one way or the other. Sometimes we call it phase or shift, frequency deviation, where it deviates just slightly. And it's a very small amount, but it is enough where the receiver can detect that and be able to detect the audio. Now, there's another term that you might read about in the book. It's called phase modulation, which is a little bit different. It's a different method of doing it, but it still comes out the same. So in phase modulation, it basically takes the frequency and doesn't change the frequency, but it kind of squeezes this part together and squeezes this part together. So now we have a higher frequency here, a lower frequency here, a higher frequency over here, and the receiver can't tell the difference. It still sees it as a frequency shift. Even though we're not actually shifting the frequency, we're just shifting the phase of it just slightly on one side or the other. And the audio is causing that phase shift. Okay, and one other thing I wanted to point out to you, there's another thing in the AM world. There's called sidebands. You've probably heard that term before. CBs used to have sidebands. You could talk on upper sideband or lower sideband. And when you get down in some of the lower frequencies, it's a common thing. The scope doesn't show it very well, but you can see this is the carrier right here. This is what I'm transmitting on. The sideband only appears when the voice is being applied to it. Test, 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 test. Now the sideband actually appears right here and right here. You can get here where we can point it out. So the sideband will actually appear right there and right there. Now you can't very well see it in this, but when you talk on the voice, that sideband will come up. Test, 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 1, 2, 3, 4, 4. You can see just a little bit of it there. But that's what we call the upper sideband and the lower sideband. This one right here is the upper sideband, and this one over here is the lower sideband. It's on either side of the carrier frequency. And we can actually talk on those sidebands. A lot of people like to use it because you can actually talk farther on a sideband than you can on FM or AM. So if we go back to the classroom, I'm going to talk a little bit about that sideband and also the frequency modulation and the amplitude modulation. So let's switch back now.
Okay, so let's start out with the amplitude modulation, or more commonly known as AM. And this right up here represents the carrier. So when we transmit, it's generating this RF frequency over the air, and it's just a frequency. There's nothing on it. Now this represents the audio. Audio is a very low frequency, and the audio is going to change the amplitude of the carrier. So it's going to come out like this. As the audio starts to go up like this, it causes the carrier to get stronger and more power. Then as the audio drops down low, it causes the carrier to reduce the power output. So it's actually fluctuating the power. There's more power here, less power here, more power here, and less power here. And even though the audio is not present, you can actually see it's almost like a footprint. See where the audio, the impression of the audio is? So this is called amplitude modulation. And it was the very first form of modulation that came out. The very earliest voice modulation. And it's still used today. There are still AM radios. Now let's take a look at the FM radio. First, okay, this is that single sideband that I was telling you about. This is kind of a diagram of it. Okay, this is the carrier frequency. This is when you just key the transmitter, that comes up, and you can see it on a monitor. Okay, Now, every transmitter has sideband noise. That's a common thing. Even if you have a commercial radio, you know, a high-end radio, it still has sideband noise. And it's on either side of the carrier. But as the frequency gets farther away, the sideband noise gets less and less and less, and it actually disappears after a while. Okay, when we talk on a AM radio, we actually get these sideband transmitters. And as I showed you on the scope there, you could actually see with the voice, but it's only with the voice that causes these sidebands to appear. And they have learned that we can actually talk on the sideband and push the carrier down so that all of the power that's going out is all just pure modulation, which is why it can travel farther than an AM or even an FM signal, because there's no wasted energy. All of the energy is in the modulation. So what we do is we suppress the carrier. As you can see, that's down here on the left side. This was the carrier we saw earlier. So we've pushed that way down so there's hardly any of it, and we've amplified the single sideband. So this one would be upper sideband because the carrier's here, and so this is on the upper side, the higher side, higher frequency side. And so we can actually talk on this. And a lot of people like to use it, especially down in the HF bands. And then if we look at the other side of it, this is the lower sideband, because here's the carrier right here, and we've suppressed it. We've pushed it way down so that it's hardly putting out any power at all, and we've amplified the lower sideband. So now all of the energy is in this one, and this is called the lower sideband. And both of these are referred to as single sideband modulation. And they're used quite a bit, really. Usually once you get down into the HF bands, almost everything is a single sideband. It's either upper sideband or lower sideband. But that's how we do it. And it's not terribly hard to do. In fact, some CBs even have that capability where you can have either upper sideband or lower sideband. Okay, so now let's talk about frequency modulation. And most everything from about 2 meters and up is all frequency modulation. Um, there really isn't any AM modulation at all in the higher frequency range. And once again, this is the carrier. And when we key the transmitter, we're just broadcasting an RF signal, a radio frequency signal, and which is represented by this. And this is the audio. And audio is a low frequency, it's a low frequency tone basically, but it's, you know, from our voice. So in this case, when the audio goes low, it causes the carrier to increase frequency. It becomes a higher frequency. Then when this goes up high, it causes the frequency to shift low. It becomes a lower frequency. So we go from high frequency to low frequency to high frequency to low frequency and so forth based on this right here. It corresponds to this. And the nice thing about this, well, there's actually a lot of advantages. When you have an AM carrier, if there's any static electricity in the air, like if you drive near a high power power line, you'll get a loud buzz in the radio. Or if there's any lightning in the background, you can hear the lightning on your AM radio. That's because any interference with the signal is translated to audio, and it comes out into the audio of your radio. But FM, that doesn't matter. You can put all kinds of interference in here, and the FM doesn't matter. Because it's only looking at the frequency shift. I mean, you can cut this down to there's almost nothing there, but as long as it can see that frequency shift, then it will demodulate into the correct audio. So FM is a lot cleaner, a lot better sounding audio than the AM is. And like I say, most everything up in the higher frequency range is all AM. And before television went digital, television was also AM or FM as well. But now it's all digital, so that's a whole different technology. Okay, there's another term called phase modulation, and it's really the same thing. It's still FM modulation, frequency modulation, but it's a different method of generating it. And basically, as like I showed you there, see this is the carrier here, and this is the audio. And when the audio goes high, it kind of squeezes this together a little bit. When the audio goes low, it spreads it out. When the audio goes high, it squeezes it together. So it still gives that frequency shift, higher frequency, higher, lower, and so forth. And the receiver at the other end can't tell the difference. So they're saying here, this is FM modulation and this is phase modulation. So it's really the same thing once it gets over the air. It's just the method of how they're doing it. And when we get into one of the later classes this week or next week, I'm going to show you how a radio actually works, and I'll show you why they do it differently. Parts of it are FM, or I mean, yeah, parts of it are true FM and parts of it are phase modulation. Okay, I'm going to show you this. Now, there's nothing on the test about digital modulation. There are no test questions, but I thought you might be interested to see it because this is up and coming technology. And we're actually starting to see digital in ham radio now. We do have digital repeaters and digital radios available. Not a lot of people have them, but it is available. So I'm going to show you how it works. Basically, if you're familiar with what's called voice over IP used on the internet, it basically takes your voice and converts it into digital. And digital is just a series of ones and zeros. It's all made up of just ones and zeros. And we're somehow transmitting those ones and zeros over the air so that the radio at the other end can decode it back into audio. So the way we do it is we have, this is our frequency spectrum here, and this is our carrier frequency. This is the frequency we're transmitting on. Okay, we can cause the transmitter to shift 1 kilohertz above the carrier and just very quickly, momentarily transmit on that frequency. And that represents a 0, 0. Then if it shifts down low, on the low side, 1 kilohertz, and again, just momentarily keys up on that, that represents a 0, 1. And then we can go 2 kilohertz above the carrier and momentarily key up, and that represents a 1, 0. Or we can go 2 kilohertz below the carrier, and that represents a 1, 1. So if we have our string of data that's coming through the radio, it's going to look something like this. So we start out here, the first, it looks at the first 2 digits is a 1, 1. So it shifts 2 kilohertz low and just momentarily keys up on that frequency to represent a 1, 1. Okay, then it looks at the next 2 digits. The next 2 is a 0, 0. So we shift 1 kilohertz above the carrier and just momentarily key up, and that represents a 0, 0. And the next one is 1, 0, 0, 1, 1, 1, 1, 1, 0, 0, and so forth. And it just keeps shifting and keying up, and those represent ones and zeros. And that's how we transmit it from one radio to another. And then the radio at your other end, the receiver, can take all that digital data and convert it back into audio so that you can hear it on the speaker. So, like I say, there's nothing on the test about it, but I thought you might be interested to know how we do that. Okay, now they can actually take that same technology and expand it out to 16 places. There's 8 on each side, 8 above and 8 below. And now each pulse represents 4 bits of data. So if we take, like here's our string of data, now it can look at these 4 bits here, 0, 0, 1, 1, and 0, 0, 1, 1 is Oops, where is it? 0010. Oh, there it is, 0011. So we shift 2 kilohertz below, momentarily key it up, and that represents those 4 bits. So now we can send data twice as fast because there's twice as many pulses, and each pulse represents 4 bits of data. And we can actually expand it more than that. We can go more and have so that each pulse represents 8 bits of data, but it's very wide. It's very broad, which is why we call it broadband, because it can spread real wide and it can send a lot of data really fast by having more pulses, and more in each pulse represents more bits of data. So that's how we get the transmissions to go faster and faster. And usually cell phone is they're very wide. They can transmit a lot of data very fast. Okay, there's a thing called DMR. You're going to hear about this in ham radio. Some people have it, and that means digital mobile radio. And there are some around. There are some repeaters that are DMR, and there are digital radios available, but they're a little on the spendy side. They're typically going to be at least $100 or more for a radio. But that's new technology. It's up and coming, and people are starting to get into it little at a time. So, at some point in time, you might want to get into that. There's some really cool stuff about it. Okay, well, oh, we're right on time tonight. Okay, so I think that's as far as we're going to go tonight. I don't want to overwhelm you too much, but I think that we're done with the math. Those are the only other formulas today, is the frequency wavelength formula. So if you remember the Ohm's law from last week and the frequency wavelength from this week, you got it made. Okay, so our homework assignment for this week is chapter 6, communication with others. And that one's not too technical. It's basically how to talk to other people. So I think you're pretty much through most of the licensing and regulations and that type of stuff. So I would really encourage you to take some more practice tests. The more practice tests you do, the better you're going to do on your test, because you're going to see more and more of the questions. And those practice tests, those are the questions on the question pool, or in the question pool. So you're going to see some of those very same questions on your test when you're going to take it. So I'd really encourage you to, do lots of practice tests. I get some people that take 2 or 3 or 4 times a week. It just helps you learn it quicker and easier. Okay. Oops, where am I? Okay, I think that's about it for this week. Any questions? Anything that we missed? Is it clear as mud?
Hey Dale, it's Frank. I have a question on single sideband radios in a maritime environment.
Yes,
How come the FCC, I guess more recently, said that operation of a single sideband radio in a maritime environment, you don't need to have the traditional ham license?
Well, you can't. There are single sideband radios that are not in the ham radio spectrum. I know the military has used them before, and there's other organizations that use them. So it's not limited to ham radio. There's others that can use that same technology.
Thank you.
Okay. Any other thoughts or questions?
Thank you, Dale. We sure appreciate all your hard work.
Okay, well, thank you for coming. I appreciate it. These classes are kind of fun to me. I hope it's fun for you. Of course, it'll be a lot more. It'll be a lot more fun when you don't have to study for a test. Okay, so I think that's all we have for tonight. And I'll get
Thank you, Dale. Have Have a good night.
You're welcome, and I'll get these videos out tonight. I'm gonna go ahead and shut it off.